Well, then thank you all for coming today. I can see many heads on the camera, so I think the room is quite full. Thank you all for coming for the talk. It's quite unfortunate I could not come to Turin because of my medical condition that got worse. But yeah, a big shout out to the organizers that they managed to get this hybrid setting running, and hopefully you'll get something from the talk, and maybe we will meet personally sometime later at other conferences or next year again in Turin. So if everything's fine, I guess I can start with the talk then. So again, who am I? My name is Andrej. The pronunciation was more or less right, Andrej Danis. I'm originally from Slovakia, but I moved to Vienna for my studies, and I've been living and working in Vienna over the past 5.5 years. I am a Finnish master's student from the Technical University in Vienna. Obviously, I'm also presenting you my master thesis right now. I'm also working as a security manager at Bosch Engineering, where we do automotive cybersecurity stuff, mostly risk and threat analysis and stuff like that for small series auto manufacturers like Alfa Romeo, Ferrari, Aston Martin, Porsche, and so on. Some of my favorite stuff is automotive security, CTFs, hackathons, and braking stuff. That's my favorite thing. So, let's start with the topic. What does actually HbbTV stand for? It stands for Hybrid Broadcast Broadband TV. It's a very complicated name for something that's actually quite easy to understand. It's a combination of broadcast and internet on a smart TV. It was developed as kind of an sub-protocol of DVB, which is digital video broadcasting. I think all of you can know it from under the name digital TV. It's just a protocol defining that the TV channels are broadcasting video in MPEG streams. And as a part of this, DVB protocol, HbbTV was made as a sub-protocol that was originally designed to kind of increase the interactivity between the TV channels and the viewers of the TV channels. How it works, the content providers, or the TV channels in this case, they define a URL in the metadata of their TV stream. This URL gets parsed by the Smart TV, and the Smart TV, if it is compatible with the HbbTV version the TV channel is using, is opening this app. So it pulls the app from the internet and opens it either on the foreground or on the background. That is then defined by the TV channel, what they want you to do with the app. HbbTV is quite widely deployed in Europe and in Australia. Some example numbers, in Italy, there is 8.9 million of households that have an HbbTV supporting Smart TV. When we are talking about security of HbbTV, we need to look at two things or two sides. The first one is the hardware side of security, mostly signal hijacking. This was already quite popular in the 80s with the Captain Midnight incident and Max Headroom incident in America. But also lately, in a DevCall talk in 2019, Pedro Cabrera Camara did a similar attack, also combining HbbTV. And he used, as you can see on the picture on the bottom right, a drone with a HackRF, which is a software-defined radio, and he flew over an terrestrial antenna. And by broadcasting from the software-defined radio, he was able to hijack the signal going to the TV that was connected to this antenna. So big shout out to Pedro Cabrera Camara, because he was actually kind of like the main talk that we based our research then on. The software part is then HbbTV specific. As I said, there is a URL defined in the stream. The biggest problem is that this URL is unencrypted in the DVB stream, and also its integrity is not checked in any way. So an attacker can just create a custom URL and inject it into the existing metadata, which then leads to the fact that the Smart TV executes or launches a web app from another URL. And in previous talks, it was already proven that this can lead to phishing attacks, Bitcoin mining attacks, or just overlaying some fake news over the existing broadcast. Currently, the state of the art is quite large. There is a lot of theoretical research on smart TV security and DVB security and web browser security and stuff. But we found out that there is very little research into like practical exploits of the smart TVs. And that was basically our motivation, that we wanted to look at the built-in web browser vulnerabilities, but of the web browsers that are used for HbbTV, because usually these are different from the usual web browsers, but I'll get to that later. So our research questions, or what we actually wanted to get, was first, how can HbbTV apps be exploited? What can we do with them? The second one was if updates actually patch the exploits, or if there are actually any updates for HbbTV. And the third thing we wanted to get was if the exploits are also working on other different vendors' TVs. So not just Android or just specific TVs, but also to look at Samsung or LG that are also using other operating systems than Android. How did we choose the targets of evaluations, the TVs that we tested our exploits on? First, we needed to consider the time scope of diplomacies, which is quite short. So we chose just 3 different smart TVs. Then we asked ourselves, what do we have actually on hand at the university? So we had a Toshiba Android TV and a Samsung Smart TV on hand. And then we asked also, what's the current market share of the operating systems? So the largest market share currently, or at least in Europe and in Austria, has the Tizen OS, which is on Samsung Smart TVs. Then the second one is WebOS, which is running on LG Smart TVs. And then Android TV is running on most of the cheaper to mid-end smart TVs from various vendors. Also, we wanted to get something that people in Austria buy. And people in Austria also buy only mostly Samsung and LG TVs, but also cheap Android TVs from Amazon are quite popular. Here is just a sample graph, just showing the TV ownership by brand in Austria. As you can see, a lot of people own Samsung or an LG TV, but also these, let's say, cheaper Android-based brands are also quite popular. So the first TV that we took a look at was this Toshiba 24 something something, very generic TV based on Android TV, which is a modification of classic Android. It was a model year 2021. So not the newest, but still quite popular. We took first a look at the firmware. We analyzed it using an Android debugging bridge, the ADB tool. Unfortunately, a lot of stuff was read-only. We were not able to fully pull the firmware from the TV, but we found out that the TV is using patches from the 1st December 2021, and we then later updated the TV, and we found out that the updates have actually no influence on the live TV part and the HbbTV part of the TV. So firmware updates were only fixing stuff on Android and on the app side of the smart TV, but HbbTV was not influenced in any way. During the firmware analysis, we actually found out an interesting thing, that there were a lot of similarities with different vendors. We were looking over some binaries and some native libraries that were used in the application of the live TV. And we actually found out that the TV is a Vestel MB171, and this TV is made by this Vestel Chinese company, and this TV is rebranded under multiple different names. So in German-speaking area, it's mostly Toshiba, Blaupunkt, and Grundig. And these look slightly different, but all of them use the same firmware and the same internals. So we actually, by pure coincidence, chose a TV that is quite relevant because it has a huge market reach. So as for updates, the TV received surprisingly a lot of updates. There were multiple security patches for Android 9, and also there was an upgrade to Android 11, which was the last update that the TV received from 1st of January 2024. But as mentioned, this had no influence on the HbbTV part, so not that interesting for us. As I said, no changes to HbbTV. The behavior of the TV was the same user agent was used, the same Chrome version, and all of the JavaScript APIs were the same. So that part was not touched any way by the patches. So we took a look at the browser that is used for HbbTV on this TV, and we found out that it's actually using Chrome 55, which is from 2016. Which we consider quite old, even for the standard that the TV was made in 2021. And we verified this by testing JavaScript APIs, and because we thought maybe the user agent is just lying, but no, it's really Chrome 55 from 2016, which at the time of writing the thesis, there were 2087 known vulnerabilities, out of them 64 were remote code execution. So this was already kind of a first sign that something might not be fully okay with this outdated technology. We found out that the TV is using HbbTV 1.5.1, which was kind of confusing because HbbTV for some reason is using two kinds of numbering. We still don't know why, because it's just confusing. Actually, it was HbbTV 2.0.2 that was released in 2018. We also found out that the browser is different from the web view, which confirmed our initial assumption that the browsers used for HbbTV are different from the web browsers that are used by the users to just view traditional web. For example, we fingerprinted the browser that the YouTube app was using, and that one reported the version to be Chrome 90. So that already hinted to us that the whole HbbTV thing might not be reusing parts of the system that are already existing under Android. We also then analyzed the functionality of the browser in HbbTV. We found out that there are no installed plugins. Only HTML, CSS, and JavaScript files are interpreted. And surprisingly, only text files and images can be opened in the browser. I think all of you know or use even browsers as kind of PDF readers, but PDFs were not allowed to show in the browser. And also no file downloading was allowed, even though there is a method for this in the API, but somehow it was disabled. But I'll get to that later. As for the second TV that we were inspecting, it was the Samsung UE something something something. It was a generic TV that we use in almost every seminar room at the TU. So yeah, we had a few pieces of them to test. It's using the Tizen OS, and it's a model year 2017, so quite older, but actually still quite popular on the Austrian market. We had this firmware version installed. It was the latest one, so there was no inspecting what's happening there after updates. And we also analyzed the browser. In this case, there was no browser version in the user agent, so we had to estimate it just by trying out different APIs that changed over the lifecycle and over the updates of Chrome. And we estimated the Chrome version to be somewhere around 44 to Chrome 55. So approximately from the year 2015. Surprisingly, the TV was supporting only HbbTV 1.2.1, which is from 2012. That was quite old. And it similarly had limited functionality, so no downloads, no PDF files, just pure HTML, CSS, and JavaScript. What was additionally kind of surprising to us that the TV was blocking requests to different origins. So if you in code did a fetch request to different URL, then the URL that you got the HbbTV app from, the request was just blocked without any error message, without anything. So probably Samsung did try to implement some security mitigations on this TV. As for the third TV that we were inspecting, it was this LG UR something something. It's a very new TV. It was the most top-selling one on Amazon in Austria. It's a model year 2024, so very new, and is using the WebOS operating system. The firmware was also, like in the previous case of Samsung, quite difficult to analyze because WebOS by default does not allow for debugging, and you have to get a developer account and you have to get approved, and so it's quite complicated. But we updated the TV to the latest WebOS version from October 2024, so we can do the experiments on the latest firmware with the assumption that LG patched everything that they knew. As for the browser analysis, it was using the newest Chrome version, which was finally something good, using Chrome 94 from 2021, which is kind of outdated, but still the newest out of the three. And it was using HbbTV 1.6.1 in the translated to the actual version 2.0.3. It was also the same version as the built-in web browser. So that one we could not kind of verify if it's just a coincidence or if the TV is sharing the same browser for two functionalities. But yeah, the built-in web browser app was the same. Also, same functionality as the primary target of evaluation. So HTML, CSS, JavaScript is interpreted, text files, pictures can be shown, but no PDFs and no file downloads. So now we get to HbbTV. Here in this very fancy table, you can see some versions of HbbTV. You can see the first version was released in June 2010, and approximately every 2 to 3 years, some updates were following, mostly implementing some support for some TV stuff that even I still don't understand what it's good for. The latest version is 2.0.4, released in September 2023, adding voice assistant integration. I'll get later back to that. Which interesting fact is that even though HbbTV 2.0.4 was released in September 2023, there is still currently not a single smart TV that's supporting this HbbTV version. So yeah, that's kind of unfortunate. The newest that we could find was the LG TV that was supporting HbbTV 2.0.3 from 2021. So during the analysis of the actual specification, which was required before we started with exploiting, we found out several problems. The first one is that the HbbTV versions are fixed throughout the TV's lifecycle. This was first just assumed by us that it's the case because usually TV vendors don't really care about updating stuff on the TVs, but it was also literally mentioned in the TV guidelines, in the HbbTV guidelines, that the vendors just don't care about this. We consider this quite a large security risk because, of course, vulnerabilities are always present, and if they are found out, it's kind of bad that the HbbTV versions don't get updated throughout the life cycle. Also, we found out that the security requirements in the specifications are very vaguely written. They are all rather recommendations written in style, yeah, Smart TV should do X, Y, Z, but obviously the vendors don't really follow the specification, and these requirements are not really written in requirements way. Only in the latest version 2.0.4, they finally implemented some proper definitions, like it is required that the Smart TV only interacts with HbbTV apps that are transmitted over HTTPS. And last but not least, not everything from the specification is implemented, which was kind of surprising and also kind of frustrating. As I mentioned, vendors don't really follow the spec, which is unfortunate. For example, HTTP was still present, even though HTTPS should be enforced. And some APIs are available since HbbTV 1.0.0, but they're not implemented. This was, for example, the case for the downloading of files. This is an API of HbbTV since 1.0.0, but on none of our free TVs this was available. which is then like, why is it even specified when no one's actually implementing it? As for features, what actually HbbTV allows you, there is a native JavaScript part of the features. This is pure JavaScript, just as you know it from classic web development, and everything is supported. However, it depends on the browser version used. So of course, you cannot use some fancy new APIs that were introduced in Chrome, I don't know, 95 in the Chrome 60. Maybe you can, but you need to patch that in. Then there are some HbbTV specific features. These are then embedded using these embedded objects in HTML and JavaScript. And there are some considerations that need to be taken. For example, the targeted version of HbbTV, as some features only are available in later versions. For example, the voice assistants. And you also need to check for APIs at runtime, as the specification explicitly mentions that not all APIs are required to be implemented, and therefore the developers always need to check for available APIs at runtime. There is a specific API call just for that. These HbbTV specific features include many functions to interact with the TV. I call it the analog part of the smart TV. So you can use these APIs to fetch TV information, like what channel is currently being watched, what is the channel list of the TV, what's the language used on the TV, and so on. You can also change the TV channel. You can listen to key presses on remote control. Funnily enough, you can also, on some TVs, increase the volume. And you can also launch other HbbTV apps. So now to the experimental fun part that you are all waiting for. To deploy HbbTV apps, we need to do 3 steps. First, we need to prepare the DVB stream. For this, we use TSDAC, which is an open source toolkit for working with MPEG streams. You need a recording of an existing DVB stream. This one you can either get from the TSDAC website, where there are some examples, or you can just record it by yourself, which is the thing we did. And then you need to inject your custom AIT, which stands for Application Information Table, and I will show you that in a second, how you can do that. Then you need to somehow get this modified DVB stream to the TV. For this, we used a high-des USB DVB-T modulator with drivers from TSDAC and also the TSDAC toolkit to start a modulation. This is quite straightforward. There are some steps required, but in a second, I will show you how you can set it up. And last but not least, you need some place to host the HbbTV app. In my case, I used a specific attack toolkit that I developed to make it kind of easier to test the exploits. But this can be any web server, as the HbbTV app, however complex it sounds, it's just a basic HTML, CSS, and JavaScript app, or like just a basic web page. Yeah, this on the right, this was our experimental in quote setup. We had a DVB modulator connected over USB. Then from that, there was an antenna cable going straight to the TV, where we launched the TV channel, and the TV was fetching over the internet via HTTP from the laptop, the web app, and that was then launched. So how I can actually do that? A practical example. So first, to inject the required stuff into the DVB recording, you need to get the service description table. This is kind of like just a table that describes like what channels are in the broadcast. This can be done by using the TSDAC toolkit. So as you can see, we have the channel recording, then we specify that we want to get the table with the number 0x42 and save the output. This is an example of the file. Of course, it's very, very long, but here in the service description table, you just take the service ID by the service name, so by the TV channel that you want to inject your app into. You write down this service ID, in our case, the 0x0051, and then you need to fetch the program map table. This program map table is another metadata that you need to get another information from. So again, you just specify the recording, then that you want the table 0x02. And in this file, you look for the service ID that you found out from the previous table. And here in this table, there are specific components defined for each TV channel. So as you can see, here is some metadata, then there is the components, there are the component streams with some metadata about the language. But the thing that is of interest for us is the application component. So from here, we just take the PID and we write it down. And then finally, we get the application information table by just pulling the table with the ID we took from the previous step. And from this table, we finally have the important information. So this is the metadata file that defines the URL and metadata about the HbbTV application. Here, you just need to rewrite the URL base to point to your URL of your selection, and the simple application location descriptor completely on the bottom, where you define the initial path of the application. You can then also change the application name, change the language of the application, define the version of HbbTV, priority stuff. For like more information about what this metadata does, you can visit the HbbTV developer guidelines. They are actually quite well describing every single metadata what it's using. But for our experiments, it was just enough to change the URL and the initial path. Then you have this modified application information table, and you just inject it into the channel recording. So again, you take the channel recording as input, then you inject into the table with the ID 0x15E1, which we took from the program map table. And we define an output of the channel recording with the injected application information table. And then afterwards, we just need to modulate it. So again, you just take tsduck and you define the input file. In our case, we also defined that we want to have the channel recording modulate infinitely in a loop, as our recording was just 30 seconds long. So that's not enough for our experiments. And then you just define your output. In our case, it was the high-des modulator, the frequency, and then some guard interval constellation, high priority. I don't know what all this stuff does. I just copied it from a Stack Overflow post. It's some very specific metadata and some very specific settings for the modulation. But because in our case, we are just modulating straight to the TV, we don't really need to define any of this. It's just important to define the frequency correctly so that your TV can actually scan for the channels that are injected. Maybe good to mention is that now this looks kind of complicated and a lot of manual stuff, but this can actually be kind of automated in such a way that you can do this with a computer with enough power in real time with only small delay. So this whole attack can be done in real time, that you take live a recording of a live broadcast, you in real time inject your own application information table, and your own HbbTV, and then you modulate this further. So for the victim, there would be more or less no way of noticing that they are being attacked. As for the attack toolkit that I used, it's just a simple Python web app, Python app that I developed to automate the attacks. It's using Python and JavaScript, Python on the server part, JavaScript on the client part, and the toolkit is communicating over WebSockets with the TV. So the attacker can live just switch between attacks and interact in real time with the attacked smart TV. The toolkit is modular and is open source. So in case you are interested in reusing that, in my thesis, there's a link on GitHub, and you can just pull it down and create a fork or whatever you want to do. So finally, exploiting. We created some kind of a realistic threat model that we wanted to exploit. In our threat model, we had several assumptions. The first one was that the TV receives the DVB signal in an unprotected way. This means that the attacker has some way to inject their own signal into the TV. So this is either using the drone that I've shown at the beginning of the presentation, flying a drone with software-defined radio over an antenna, or maybe even a better way is to just hook up your modulator directly to those distribution boxes that you can find in front of buildings. And this way you just inject signal to all of the TVs in the block. We also assume that the smart TV has no malicious apps installed, of course, and we also assume that the attacker has some kind of basic knowledge of the target, so that they know the version of the operating system, the version of the HbbTV that the TV supports, and a very important thing, which channel is currently being watched, because if you want, as an attacker, for the attack to launch automatically, you need to inject the HbbTV app exactly into the channel that's currently being watched on the TV. So as for the threats, the first one is denial of service. So that's quite self-explanatory. Black out the screen, showing something else, blocking the video output, blocking the audio output, or blocking just the controls of the remote control. Then we have spoofing. This could be just switching the video, but leaving the audio intact, or the other way around, leaving the video, but switching the audio track, so the victim will not get it that they are listening to something else. Or another case of spoofing could be that we use an overlay news banner and write some fake news over the actual news without the victim noticing. Another threat could be phishing. This is quite common, just showing a pop-up saying, okay, password to your Wi-Fi network changed, please put it again. Or quite common is that HbbTV apps are used for teleshopping. So actually a lot of people surprisingly are putting in their credit card information into the TV, which is kind of not secure in my opinion, but you do you. And you could just show a phishing prompt injected to some teleshopping channel like, oh, you need to update your credit card information, and then you have the credit card information. Last but not least, the most interesting threat for us was the local network access. This means that the attacker could use the smart TV as a kind of proxy to interact with devices that are connected to the local network, and that would normally not be accessible from the internet because they are, for example, behind a firewall. This could be a huge security risk in case there are some IoT devices on the network that usually are just locally accessible and they don't really have security features implemented. An attacker could access them, and like one example could be a IP camera that could the attacker fetch some pictures from and just download them through the TV. We were successful with those threats, but we were also unsuccessful. There were two threats that we were not really able to exploit. The first one was peripheral access. We were interested in knowing whether an attacker could spy on you by listening over the microphone or by taking pictures over the web camera of the smart TV. However, this was unsuccessful using the native JavaScript APIs because all the requests for the camera permissions or for microphone permissions just failed without any error message. So our assumption is that the HbbTV web browsers have some kind of patch that just blocks all these requests. And also in HbbTV itself, there is no API that allows for hooking up to the microphone or to the camera. Theoretically, in HbbTV 2.0.4, now I return to the voice assistants that were introduced, you could theoretically misuse that feature, and you could, because there in the specification, there is a mention that you could use voice assistants as a ways of input into your application. So you don't really have direct access to the microphone, but you have that kind of direct access through the voice assistant. But we were unfortunately not able to inspect this because, as I said, there are no TVs currently with HbbTV 2.0.4 on the market. So if maybe someone of you wants to follow up on that, just wait on a TV that supports HbbTV 2.0.4, and it will be definitely interesting to see if you can use voice assistant to spy on people. The second threat was remote code execution. We were quite sure that the vulnerabilities for remote code execution are existing because they are in the databases. The browsers are outdated. We also tried some known RCE exploits for Chrome versions before 94, but all of them are quite specific for the platform. So most of the remote code execution exploits that are already like ready to use are mostly for Windows or for Linux, and just for x64. In our case, our smart TVs were ARM, and two of them were just ARM 32-bit. Some of the exploits crashed the browser, but we were unable to craft a shellcode that would actually correctly run on the smart TVs. Because of the whole time constraint of having this done as a diploma thesis, we did not follow on that, but I am quite I think it's really possible to craft a working shellcode and have a remote code execution on the TV. One of the kind of examples could be the Samsung Q60T exploit, which is a routing exploit that's using the built-in web browser to route the Samsung TVs. Unfortunately, our Samsung Smart TV was not compatible with this exploit, but because it's using a web browser and HbbTV is also using a web browser, we think that this exploit could also be done over HbbTV and could be modified in such a way that you route the TV and then launch a reverse shell back to you. So this is also something that could be tried out. So as for the results, on our primary TV, on the Toshiba Android TV, all attacks were successful. We found out that the firmware updates have no influence on this. Both Chrome and HbbTV versions stayed the same. We were able to do all the attacks, denial of service, spoofing, phishing, and we were also able to interact with devices on local network and do kind of network scans over JavaScript through the browser. So that's that. Here would be a video of the exploits, but I decided not to show that. Here is a QR code. If you are interested, you can now open it up in YouTube and save it to view later. Or you can then write me a message later and I will send you the video again. It's a 2-minute, 30-second video just showing up the attacks on the Toshiba TV. As for our Samsung TV, a local network access attack was not successful, but all the others were. This was due to two reasons. The first one was that the browser was very, very outdated, and our network scanning library or feature of our attack toolkit was not running properly on the smart TV, which we theoretically could patch and fix, but the TV anyways blocks any request to different origin, so you could not interact with any devices on the local network anyways. So Samsung, I don't know if this was intended, but they protected themselves against this type of attacks. Anyway, still the browser is very outdated. As I already mentioned, the other Samsung TVs are vulnerable to a JavaScript type confusion attack, which is used for routing. And I'm still kind of positive that this attack could be reused through HbbTV. As for our third TV, the LG TV, again, all attacks were successful. Some little adjustments were required for denial of service and spoofing attacks. This was because in Chrome 94, the APIs for media access changed a little bit, so it's not allowed to autoplay your own videos. However, you can kind of go around that because Chrome by default whitelists YouTube for autoplaying. So you just need to upload your video to YouTube and then just put an YouTube iframe over full screen, and then you can just launch any video you want. As I previously mentioned, this was the most up-to-date TV and implement some modern protection mechanisms, but still this does not protect against these type of attacks. Of course, the most important attack, the local network access, was again successful, and we were able to interact with devices that were connected to the local network. Okay, so that would be almost all. There's some conclusion to this. First one is that HbbTV is actually quite a pain to work with. This is because the specification is kind of incomplete. There is vendor-specific implementation, so vendors don't really follow the specification, or they just do stuff on their own. And there is also the problem of slow rolling out of updates. And this is also kind of unfortunate because it complicates the whole development also for developers. Also, security requirements are very vaguely and inconsistently implemented. They also use some very risky security assumptions. For example, there is a specific sentence in the developer guidelines that's mentioning that HbbTV itself as a protocol is always based on 3 years older web technology, which is kind of confusing. Why is this the case? But we find this quite risky to say, and to base something on 3 years old. Like, I don't know why they do this, but yeah, they mentioned that this is because of compatibility with other TV models, as they specifically mentioned that usually in Europe, the kind of lifetime of a TV at home is usually 6 to 8 years. So most households change their TV after 6 to 8 years, and they want to kind of make the HbbTV protocol compatible with most of the TVs. But because of the other reason, that the HbbTV version that's fixed throughout the TV's life cycle, we find this kind of insecure. Anyways, smart TVs are usually updated just the first 2 years of their life cycle. And this is kind of something to think about, if it's really secure to leave something connected to your local network and to the internet that's not receiving updates for further 4 to 6 years of its life cycle. Me personally, I would not do that. And also the professor that were listening to my defense of this thesis, they also said that they are immediately disconnecting their TV from the internet. Last but not least, there is kind of a huge potential for large-scale attacks. State-backed actors have enough resources to do the signal hijacking and injecting of custom HbbTV apps, or kind of in a large scale. We for sure know that small attackers are using like those drones, or they hook up to the distribution boxes in the buildings, but state-backed actors could do hijacking over satellites or just hijack the local TV broadcasting stations. So because of the large amount of vulnerable TVs, there is a potential that state-backed actors could misuse this and launch kind of large-scale attacks on infrastructure, for example. Just imagine that the millions of TVs that are in Europe now start doing a denial of service on a, I don't know, on something, on hospitals, for example. That's going to be quite an issue. That would be all from me. There are some takeaways that you can take from this talk. I hope it was kind of understandable even in this hybrid setting. In case you have any questions, or you want to see the thesis, or you want to cite the thesis, or you want to discuss anything, also not really HbbTV related, but also car security or another cool security stuff, or you want to talk about job offers and stuff, just add me on LinkedIn, or if you don't like social media, just ask the organizers. I'm hereby allowing them to share my email address with anyone that's interested with talking to me. Yeah, so that would be everything. Thank you for listening, and I'll be happy now to answer any questions.